Hi, this is Darren, and today we're going to talk about decreasing ingestion congestion using Intel Optane DC persistent memory. Before we dive into it, I want to first go into a little scenario that we ran into with some of our customers. And this is the automotive industry. The automotive industry right now is in the middle of a major paradigm shift from being just a manufacturing type of company into being more of a service type of company. We're seeing driverless cars with autonomous vehicles. We're seeing shared models. We're seeing both driver-based shared models and owned cars. So there's a whole myriad of new things that are happening. And what's really cool about that is there's a lot of data that's being generated. And one thing that these automakers are trying to figure out to do is, what do I do with all this data? So we've, at Intel, have helped develop an automotive data center architecture blueprint, which gives them some ideas on how you can build this intelligent connected vehicle architecture so you can handle all the data coming from these cars, analyze it, and then tie it into the other aspects of your automotive business, whether it's HPC computing for new vehicle design and simulation, whether it's making your digital factory smarter with a nice feedback loop from the cars, whether it's targeting your customers more effectively with your CRM cloud, or whether we're doing autonomous vehicle design. So we first started looking at, all right, what can connect to this intelligent connected vehicle? And car companies are looking at this as well. They're trying to figure out, how can I monetize some of this data? Not just by selling new services to the people buying my cars, but maybe selling data to other people as well, like the weather company. Imagine I've got 100 million cars out on the road, all with temperature and pressure sensors on them, and they're driving all over. Wouldn't it be cool if I could sell that information to the weather company to get more accurate data on the weather in a city or in a country? Really cool kinds of technologies. Or I'm doing dynamic mapping of the roads to find out where the potholes are, or a ladder in the road, or maybe I'm doing alert systems if there's an accident that I can automatically send an ambulance out immediately instead of waiting for someone to call. The possibilities are becoming endless on things that we can do with the type of data that we're gathering from these cars. So let's take a look at a high-level picture on what this architecture looks like, and you'll find out from this where the problem that we're trying to help them solve is. So high level, I've got my connected car cloud, where I'm connecting the cars into the data center. And then on the right-hand side, I've got all these connection services that connect to external systems or other data centers inside my own ecosystem. So there's a lot going on here. There's a lot of services. I need to cleanse data, annotate the data, store it. I need to link it, augment it. There's a lot that can and does happen here. So if we take a look at all these services and how they all work together, you can see they all start at one point, which is data ingestion. This data ingestion part happens to be a bottleneck right now. Now you'd say, well, Darren, data ingestion, that's no big deal, right? I mean, we've been doing data ingestion in other industries for a long, long time. But I want you to think about having 100 million endpoints that are all producing data that needs to get into my data center. Now, that's a tall order. So most people, when they talk about data ingestion, they are using a technology called Kafka. Kafka was developed at LinkedIn and is open source now. And the basics of Kafka is it's a producer, consumer, or publish and subscribe bus, right? That's been optimized for high throughput, high number of messages going through. Okay, and this is its simplest form. There's a lot more going on, but for our purposes, let's just talk about it at this high level. So cars could push data into a producer, and the producer would then analyze just that data just a little tiny bit, like what make and model of car it is, and then it would publish that message onto a Kafka bus via Kafka server. and it would publish it on a specific topic. And then the consumer microservices on the right would subscribe to a specific topic. So maybe the topic would be Toyota Camry 2019, right? So all Toyota Camrys that are 2019, which I could easily key off of the VIN number coming from the car, would end up on that same topic. And then the consumer knows, okay, I know what to do with data from a Toyota Camry in 2019, and it would do what it needs to do to store the data, annotate it, clean it up, whatever it needed to do. So this is the basis of what a Kafka server does. Now you'll see also in this inside I have topics, and then each topic can have multiple partitions. I have partitions so I can have high availability if one of my Kafka servers goes down, and I also use partitions in an interesting way to improve performance, which I'll show you in a little bit. So let's take a look at some of the best practices specific around the producers, because once it's in, the consumers are actually very fast. It's a read operation. It's not write operations. So it's pretty fast. But there is some optimization we can do there, but we found that the bottleneck is primarily on the producer side. How do I get all that data from the cars into the system through this kind of Kafka gateway, for no better word? So there's three major things I can play around with on the producer side. The buffer size, I can match the buffer size up to the message sizes that I have coming in. So if the message sizes coming in are 240K like they are for canned data, then I want my buffer size a multiple of that message size. That will mean that my message sizes will line up most of the time and I don't get segmentation. If my buffer size is smaller than the message size coming in, then it requires multiple writes to store one message, and that will slow me down. Now, another thing that I can do is I can play around with the batch size. This is the number of messages in the producer before I write them out to a Kafka server. So this too can be manipulated to increase performance, either up or down, depending on what your configuration is. But the number one thing that people do to increase performance is they take their Kafka servers and they spread the Kafka logs, which are a temporary storage. Now they're temporary storage, but they're persistent, right? In case the Kafka server goes down and comes back up, it can start where it left off. So you need that persistence because you don't want to lose messages. So it stores that on a file system, and then the consumer can lift it off of that file system. That's how it works in its simplest form. So if I can spread this out across multiple drives, then the drive doesn't become the bottleneck anymore because I'm spreading it across multiple drives. This technique is used in almost every optimized Kafka configuration out there is multiple drives. Okay. Here's an example of LinkedIn's configuration. If you go on to Kafka, they have these numbers published there. They're probably about 9 months old would be my guess. They can ingest about 13 million messages per second. And that equates to about 2.75 gigabytes, not bits, gigabytes per second of data. Now, their typical message size is under a K, 1 kilobyte, right? So they're able to get those numbers. Now, if you take a look at their configuration, they have 1,100 Kafka brokers in more than 60 clusters. And the clusters are handling different types of messages that are coming in, right? And they have redundancy and all those things that you really need in a good Kafka configuration. So if we take these numbers and extrapolate those numbers up to some of the things that our customers are looking at, like in the automotive space, it'll give us a high-end number of how many servers we're going to need, how many Kafka producers, or all that. And these are back-of-the-envelope numbers, not optimized, but you'll see where some optimization could come in. So one customer that we have wants to hook up 100 million cars to their data center. And if we take the just canned data, this is data that are on the sensors on the car, no LiDAR, no video, no pictures or anything, just canned data. That's about 240 kilobytes per minute per car. So if you run the math, it's about 1.6 million messages per second, which we could easily do in Kafka with the configuration that LinkedIn is doing on the messages per second. But when we talk about the amount of data throughput, we're talking about 800 gigabytes per second. That's a lot bigger number, right? So if I take that as my constraint, then, and I just use the LinkedIn configuration as is without optimizing it, I need something like 44,000 brokers or 1,000 racks of machines and over 2,400 clusters. That's crazy, right? That's not right. So if we looked at optimization on message size, buffer size, drives, and things like that, we think we could probably do a 10x performance improvement and get it down to 4,400 brokers or 240 clusters. Still, just for ingestion in the architecture, we're still talking 4,400 servers. Or around 10 racks, about 100 racks or 120 racks of machines spread over multiple data centers. Still a major cost, something that they're saying we need help. We need help figuring this out. So there's our problem statement. Now, this happened probably in January this year. I got my hands on some Apache Pass, which is our internal code name for Intel DC persistent memory, right? Optane persistent memory. It's a big, long name for it. But I got my hands on some of that, and I said, I want to see what happens if I use this memory to help in my Kafka problem that I'm having. So this is what it looks like. This Optane DC persistent memory. It comes in 3 different configurations, a 512 gigabyte module, a 256, and a 128. This is available this spring, late spring, from many of the OEMs that are out there today. It is DDR4 compatible, so it fits right in your DDR4 pin slots. It's hardware encrypted, so all your persistent memory is encrypted, high availability, high reliability, really, really cool stuff, right? When I got it, I was like, this is awesome. I have a persistent memory DIMM I'm holding in my hand. Very, very cool technology. So let's take a look a little bit at this technology, what I can do with it. So there's 2 modes of operation for this Optane DC persistent memory or Apache Pass. One is called the app direct mode. Now in the app direct mode, I can change my application to write directly to the persistent memory. And there are lots of libraries that are out there that are available that have been open sourced. So lots of languages are supported, including Java, Node.js, JavaScript, C, C++. I think even Go has some persistent memory libraries that are available today. So I could easily write an application that writes directly to persistent memory. The machine turns off and turns back on, and it's still there. I'm still in the same state I was before. Pretty darn cool stuff, right? And then there's also memory mode. Now, memory mode, I can use my persistent memory as just normal DDR4 memory, where I use the normal DDR4 memory that I have already on my server as DRAM cache, and I store all of the other stuff in persistent memory. And this lets me build out my servers at a lower cost for memory. Right? And so it's there's 2 modes of operating this, and I can change these modes of operation right from like the Linux kernel. Right? I can boot up the machine, make my changes, reboot the machine, and I can change the modes on how I'm going to use that memory. Pretty cool stuff, right? So I learned a lot about, hey, what could I do with this memory? So the first thing that came to my mind was, I'm going to take a look at Kafka. It's open sourced. I'm going to rewrite Kafka. That's the first thing that popped in my head. And I said, wait, that's crazy. That's a lot of work. I don't want to do that. What if I just increase the memory? So now I've got a 6 terabyte server. I can increase my buffer sizes to really big, right? And I can see how it will perform. So no code change, no Kafka configuration changes, just buffer sizes, and I got no change in performance. And the reason why is because I still have to write this stuff out persistently to a drive. So I got the same performance as I did without the Apache Pass or the persistent memory. So the next thing I tried to do was I went back to, okay, I'm gonna change just the thing that writes stuff out to temp space, right, to my Kafka logs. I'm gonna replace that code and jam it up into persistent memory. It was way too much code change, and it would have taken months and months and months of coding and then testing to get that done. So I threw that out. I said, no, I can't afford to do that. Then I found out something really interesting. I could, using app direct mode, right, I could take that persistent memory and I could map it to a memory drive. We've done mappings to memory drives before, but this time the memory drive is persistent, which I need. I need that persistent drive. So I could easily create a file system on that persistent memory. Now, one of the benefits I found was by doing this, I'm no longer going over the I/O bus. I'm going over the DDR bus. Much faster, much higher throughput than I get on a typical I/O bus. So I was like going, this might work. This could be really cool if I tried this out. So that's what I did. I did the low-hanging fruit. All I had to do was boot my server up and take part of that persistent memory and map it into app direct mode. And the other part I had as an extension onto my current memory. And I did that and mounted it as a file system. And then I pointed my Kafka logs to it. Pretty straightforward to do, right? So real quick, I want to show you how we set up the physical layout of the persistent memory with the DDR4. Now, the best configuration for the highest throughput is something that we call a 222 configuration. That means that every slot every duplo of slots, I guess is the right word, but for every DRAM, I have one persistent memory module, right? So for a DRAM, a persistent memory module, a DRAM, a persistent memory module, right? Or AEP, Apache Pass. And that configuration gives me the most Apache Pass as well as the most DRAM. And there's guides out there that you can look at, but for our configuration, we went with 32 gig DRAM modules and 128 gig persistent memory modules. Right? I think they normally say you only need 16 gig with a 128 gig, but I had 32 gig laying around in my lab. So I went with the 222 configuration because it gave me the most persistent memory and the most DRAM in the same configuration. Okay, I had a 2-socket system, so I was able to get 1.5 terabytes of persistent memory. Right, so pretty good configuration, right, for a server. Some of you guys are like salivating. Only 1.5 terabytes, Darren? We can go all the way up to 6 terabytes of memory with this configuration if I'm using the 512 gigabyte memory modules. So pretty cool stuff. All right, so let's get back. I was using REDHAT, and there were there's two command lines out there that you can download onto your REDHAT configurations. IMP CTL, which lets me manage the Intel persistent memory modules, and I can do that right on the command line. I can configure how they're being used in app direct mode or in memory mode. And then there's the NDCTL command, which is for non-volatile memory. This allows me to mount those drives or create drives out of that memory. And then, of course, using your normal file system like makefs MKFS to create the file system. So those are the utilities that I used. And it turned out pretty simple. I'm going to show you what the configuration looks like here in a second. So another thing I wanted to do is I wanted to run the test so that I could decrease the amount of variability that normally happens in a system. So I wanted to run my producers and my Kafka broker on the same machine. And by doing that, I eliminated the network variability that you typically get in a network, because I was seeing, where is the bottleneck? Is it with my drive or is it with the network? Well, I wanted to just isolate everything. So I isolated everything. I'm running one Kafka broker, and I'm going to run producers against that Kafka broker on the same machine. So this decreased the number of inter-broker communication because there was one broker. And I only ran producers at one time, and then I ran consumers individually, and then I ran them mixed, so I could see what the effects would be on running the different tests, right? So I've isolated it. I was trying to isolate and get specific to if the drive is going to make a difference or not. That's what I wanted to focus on. All right, so my first configuration I did was I said, okay, I'm going to take half of my persistent memory and carve it off into direct access mode, right? So into app direct mode. So I did that with this command, ipctl. I created the memory mode where I'm using 50% in app direct mode, and it carved it off. Now, it did something interesting I wasn't ready for, but it actually created two regions, and then I could map those regions onto drives, because it doesn't want to do traffic across the CPU bus between the two CPUs, because that will slow things down. So it created two regions, one for the socket 1 and one for socket 2, or socket 0 and socket 1. So I had region 0 and region 1, and then I just created a simple mount point for those and created file systems on there. So very simple to do. It required a reboot, but you know, I'm testing things out. So no big deal. Didn't take hardly any time at all. So this is really interesting. I ran a producer and I got a very similar result. No matter how many messages I passed through, the message size didn't really matter on the results that I got. They were the same. So what that told me was the producer couldn't produce data fast enough. So I said, well, I'm just going to run two producers at the same time, and then I'm going to calculate total throughput on the broker. So I did that, and I got linear results across all the different message sizes. I didn't change any buffer sizes or anything, just message size was all that was changed, right? If you notice here, I stayed pretty linear all the way up until 5 producers, and then at 10 producers, the 1K really shines because the standard configuration is optimized for 1K, right? Remember, my sweet spot was 240K. That's what I was looking at for the automotive industry, and I got some pretty good numbers there, right? When I was running 10, even out to 15 producers, it decreased a little bit, but not substantially. Not until I got to, above 20 in the 30 and 40 range. So I said, these are great numbers. Now I need to compare these numbers against running with just a normal SATA drive as the Kafka log, and against our Optane NVMe drives. So that was the next thing that I did. And I ran these on the 240 kilobyte message size. I wanted to do 240 kilobytes because that's the use case that I was looking at, right? And these numbers are quite interesting. The bottom graph is the normal SATA drive, right? And it's maxing out at around 150 or so megabytes per second. Pretty fast, but if you look at the Optane drive, the Optane NVMe drive, it's almost double that. And then look at that PMEM drive, as I call them, the Apache Pass drive, more than double that. So I'm getting approximately a 4.5, 5x performance improvement over a typical SATA drive. Pretty impressive. I was like, wow. But I was kind of disappointed that I started getting degradation, as you can see, almost 50% degradation when I had 40 producers running against the same Kafka broker. So I was like, gosh, I'm not too excited about that. I want that to be more linear, but 10 producers, this is quite substantial, right? Because I'm pulling now in approximately 500 or 600 megabytes per second on this, and it's like, wow, that's pretty impressive. If I go back and look at my initial thing that I had to look at, I need to bring in 800 megabyte or 800 gigabytes per second. So I'm still in a pretty good spot here, but I needed to find more. So that's what we have to look at. So one of the problems I was having is I kept blowing out my drives. I would fill them up so fast because I was pushing so much data to them that I said, you know what? What if I went back and I said, why don't I do 100% app direct mode? Because then I'm going to use more of that persistent memory. It says, because I want to run this test a little bit longer than what I have been to really get the numbers really locked in, right? So I shut down the machine, I reconfigured my memory, and I went to app direct mode. I wanted everything. So I put 0 in there for memory mode and 0%, and boom, I made everything app direct mode. Okay. I still had pretty good amount of memory, still have a lot of memory there. And I said, all right, now I'm going to run the same tests that I ran before. And I got a weird result. It didn't top off at 5 or 10. It actually kept going up, dramatically so. And then even when I got up to 40 concurrent running producers, I only got a small percentage decrease from the total throughput that I had before, which is now approaching 2 gigabytes. Not bits, gigabytes per second. Pretty impressive. I was like, what is going on? Did I do something wrong? I'm trying that out. I ran the configuration back to the 50 mode and back to this. And I found out that in the 100% app direct mode, I decreased the amount of contention on the DDR bus between the DRAM that was being used as cache and the persistent memory, which was being used as main memory. And I got rid of that contention. And now when I was writing to this file system, I had the whole channel open up just for me. Right? So I got incredible performance improvement. So with this, I'm now running at 2 gigabytes per second. So now, theoretically, I could put 400 servers in to ingest across several data centers. That is a lot more reasonable. I could do that. Now, we've run additional tests since then, and we know there is overhead, and it's mostly now tied to the network on having multiple brokers, so I have high availability and all those sorts of things. But we really moved the bottleneck from the drives by using this technique. We moved it from the drives now to the network. So putting in a higher speed network, like 100 gig or 40 gig instead of a 1 or 10 gig network, moves that bottleneck up higher. When we ran our test on a 10 gig network, it was capping out exactly where we thought it would because the network is now involved. So this is a really fascinating experiment in our labs, and we see a lot of really neat and interesting solutions using Kafka in different ways that we never would have thought of before, such as using it as temp space. Other areas that we're starting to do research in on this is using it for Elasticsearch with no changes to the code, just using it for the temp space. And I want you to think about all the other things that use temp space that could be causing you a bottleneck.